Today I will be presenting our work Mapping Networks, carried out jointly with Professor Samapada Mukherjee. Deep learning models today are becoming increasingly large, often containing millions or even billions of parameters. While these large parameter spaces improve expressivity, they also introduce several challenges like higher memory requirements, increased training time, severe overfitting, and complex optimization landscapes. Our work is motivated by an important observation that the training trajectories of large neural networks effectively lie on smooth, low dimensional manifolds. This gives us an intuition that all the parameters of a neural network are not independent of each other. That is, the effective degree of freedom of the parameter space is much less. Now, if these parameters lie on smooth low dimensional manifolds as shown by the plots, then a genuine question comes: is it possible to construct a mapping from this low dimensional space to the high dimensional parameter space? Because if such a mapping can be constructed, then just training a small latent vector in this low dimensional space would suffice training the entire neural network. And this is where we propose our mapping theorem, which states that yes, such a mapping function G exists that can map from the low dimensional latent space Rd to a high dimensional parameter space Rp with bounded loss. Now, to explain how the loss is calculated, this is the parameter space. Let's consider it to be the actual model. The data is fed to the model. We get the output, and based on that, in a normal way, the loss is calculated. And under bounded loss, there exists a mapping function G. Now, the practical achievability of such a mapping function G is proved by our next theorem. More about this practical mapping function will be discussed in the subsequent slides. Now, based on this mapping theorem, we propose our mapping networks, where instead of directly training all the parameters of the deep neural network, we train a smaller representation and then map it to the entire parameter space. We begin with a small trainable latent vector which is randomly initialized. This latent vector is then passed through mapping weights which are orthogonally initialized and non-trainable, but they are modulated by the latent vector itself. This mapping network generates the parameters for the target network, which means that the number of output neurons in this non-trainable mapping layer is equal to the number of parameters of the target network. The data is given to the target network, and the parameters of the target network are used for feed forward and inference only, giving us to the output y. After that, the loss L is calculated, and this loss L is optimized to train the latent vector, and this process continues until the model is trained. So, rather than optimizing the millions of parameters, we are restricting the optimization to a structured low dimensional representation and decoupling the training from the original network. This framework achieves significant reduction in trainable parameters and it lowers the overfitting. To explain the modulation of those orthogonally initialized mapping weights a bit more, this diagram is provided. The fixed weights are modulated using the latent vector via additive modulation. This M of Z is the modulating term. For our paper, we have considered a simple additive modulation, that is M of Z is equals to alpha it times Z, where alpha controls the impact of the latent vector Z. To be specific, all the mapping weights connected to this first input neuron are modulated by Z0, second neuron are modulated by Z1, and so on. Furthermore, our mapping networks can be used to fine-tune pre-trained models as well. In that case, rather than generating all the parameters, we generate a set of fine-tuning vectors, and these vectors are used to tune a set of weights, a set of pre-trained weights to be specific of the pre-trained neural network, which helps it adapt to a new task or to a new dataset. An important component of our paper is the mapping loss, which ensures smooth and stable learned manifold structure and enforces the assumptions and constraints of our mapping theorems. The mapping loss has four components. First one is the task loss, which ensures good downstream task performance. Second is the stability loss, which penalizes large output changes caused by small part aberrations in the latent vector. Third is the smoothness loss, which regularizes the Jacobian norm and helps to preserve differentiability and smoothness of the manifold. And finally, the alignment loss, which helps improve the compatibility between the latent vector and the total parameter space. We have explored two different training strategies. First one is single latent vector training, wherein a single latent vector generates all the parameters of the target network, but for larger target network, the number of fixed non-trainable mapping weights increases, which may lead to memory inefficiency. To address this problem, we assign different latent vectors to different layers. That is, separate latent vectors generate the parameters of different layers. This reduces the memory requirement and is also tightly aligned with our experimental observation. That is, the plots shown in the first slide, where we showed the low dimensional plots or low dimensional manifold plots, suggest that the parameters of different layers lie on distinct low dimensional manifolds. So if we use separate latent vectors to approximate the parameters of different layer, then the expressiveness would increase further, which is also showcased in our results, that in most of the cases the layer wise training beats its single latent vector training counterpart. The memory efficiency is explained using an example in these slides. Moving on, we have evaluated on various tasks like image classification, defect detection, image segmentation on various datasets and some inspired baselines. The results show that mapping networks achieve comparable to better performance in most of the cases as compared to the baselines. Now, an important observation is that while training fashion MNIST and the trend remains same for others as well, we observed that the baseline CNN, that is using normal training procedure, achieved a train accuracy of around 99.1%, but the test accuracy dropped to around 93%. Hence, there is a significant overfitting. But while training using mapping networks, this gap was just 1.8%. Hence, mapping networks achieved an increased test accuracy. So, mapping networks significantly decreases the overfitting. Furthermore, orthogonal techniques like pruning and low rank decomposition can also be effectively combined with our mapping networks. Low rank decomposition can help us decrease the size of latent vector further and also the number of mapping weights, whereas pruning and quantization can help us decrease the size of the target network after it is trained using mapping network. For tasks like image segmentation, where every part of the image is important, mapping networks perform worse as compared to the normal training. This is because the amount of redundancy in the total parameter set is less for such a task where all parts of an image or all parts of the data are very important. To conclude, mapping networks provide an efficient training method of the latent space and decouples training from the target space. Our method reduces overfitting, reduces training cost and memory usage. Layer wise training makes it scalable to large networks. Thank you.